Hi everybody, and welcome to exercise 2 on page 35 of the workbook. Let's read this question together. So they'd like us to answer each of the following questions and to justify our answer as efficiently as possible. Okay, so they are encouraging us to be lazy in this problem. We want to come up with the shortest possible solution that we can. Okay, and so that's going to mean thinking about some of the theorems that we've talked about, using the facts and seeing how we can put those together to arrive at an efficient solution. Okay, so take part A here, for example. They ask us the question, is the set 1, negative 2, 2, negative 4, 3, negative 1 a linearly independent set of R2? We could do this the long way by forming a matrix, taking those three vectors as our columns and going through the usual process that we go through to determine linear independence, but there's a shorter way. Okay, so it comes down to starting out by asking yourself, what is the dimension of the vector space that we're working in? Well, in our case, we're talking about R2, and we know that its dimension is equal to 2. Okay, so the question then is, can a set that contains three elements, three vectors, be linearly independent in a two-dimensional subspace? If you look back at our dimension facts, the answer to that question is no, it can't. Okay, it comes down to the fact that the dimension of R2 is equal to 2. We know that any linearly independent subset of R2 can have at most two vectors. Okay, that was dimension fact 2. Okay, so this set that contains three vectors, that can't be linearly independent by that set. So notice that we didn't have to do any calculations to come up with that conclusion. We just had to give an explanation, say which fact we're using and how we're using it. Okay, what about B? Okay, so here they're asking us, do the polynomials x squared plus x minus 1 and x squared minus x plus 1 generate P2 of R? And again, a good first step is to ask yourself, what is the dimension of this vector space? Okay, well, you look back at the table that we made, that has a dimension of 3. Okay, Pn of R has a dimension of n plus 1. And so the question is, can two polynomials generate a three-dimensional vector space? And there again, the answer is no. We need at least three polynomials to generate a three-dimensional vector space. Okay, so our explanation might go something like this. Since the dimension of P2 of R equals 3, any generating set of P2 of R must contain at least three polynomials. Okay, and if you look back, that's dimension fact 1 that we're using there. Okay, so again, we were able to answer that question without doing any calculations, just using the fact that we know that a generating set has to contain at least three polynomials, and we don't have three polynomials, so the answer must be no here. Okay, and then finally, part C asks us, can the tuple pi2e be written as a linear combination of these three vectors? Okay, and if so, can it be done in more than one way? Okay, well, we could do this by brute force, set up a system of equations, but we're going to choose a little bit different approach here. Okay, and start by making the observation that these three vectors are linearly independent. Okay, and we can do that by just looking at a system of equations. Okay, so since the system, I'm just going to form the system that we would get by making those three vectors the columns in our matrix. Okay, and noticing that that's already in an echelon form, we can see what our pivot positions are, and therefore that this has no free variables. That tells us that the columns in that matrix form a linearly independent set. Okay, so let's make a set with those three vectors as our elements. 1, 1, 0, 1, 1, 1, is linearly independent. Okay, that's a nice little fact. But we can say a little bit more here. These are 3 tuples in the vector space R3, and we know that the dimension of R3 is 3. Okay, so if you look back at our dimension facts, we've got 2 things here. We've got a linearly independent set of 3 vectors in a 3-dimensional vector space. DF4 tells us that that means that the set beta is a basis. Okay, so continuing this statement, we see that beta is a basis for R3 by DF4. Okay, but if this is a basis, we proved a theorem, theorem 1.8, that says that if you have a basis, then that means that for a vector space, that means every vector in the vector space can be written as a linear combination in exactly one way. That answers the entire question for us now. Okay, so we can finish this then by saying, therefore, by theorem 1.8, without doing any calculations, we know that this vector pi 2e can be written as a linear combination of these vectors in only one way.